All right, buckle up for this one. It's going to get a little weird. And we're going to start talking about some strange stuff. Strange stuff in this chapter, or this section of the chapter. All right, there's something called enthalpy. You've kind of seen it already. I've probably just blurted it out a few times. It's pretty close to energy, but it's not exactly energy. All right. Enthalpy, like the symbol for enthalpy is actually an H, which is kind of weird. It's like you'd think it'd be an E or something, but no, it's H. The definition of enthalpy is really weird. It's the internal energy of your system plus the product of the pressure and volume of your system. That's really weird. I mean, we can measure the pressure, we can measure the volume, but the internal energy is something really strange. Like, well, not really strange, but it's impossible to measure. All right, the internal energy, like all of your little particles, all your molecules, all your ions, whatever the heck your system is, they're all moving around. So they have translational energy. They're moving from place to place. There's also rotational energy. So they're tumbling, they're rolling, they're spinning. There's also vibrational energy. So they're like shaking and shimmying around. All this stuff. So there's all these different things, and it's absolutely 100% impossible to measure it. All right, so there's no way we can measure this. Therefore, there's no way we can measure the enthalpy. So it's impossible to measure the total amount of enthalpy in your system. So, okay, that seems kind of pointless. What the heck? We can measure changes. All right. We can measure changes in the enthalpy. So, okay, why is that useful? And how can you even measure that if you don't know the amount? So the example I always give, I always say, like, imagine you had like a really, really, really unbelievably rich relative. Say they're a millionaire or close to a millionaire. And they're like, they have almost a mole of dollars, some impossible amount. They have a whole entire section of the Grand Canyon filled with money. I mean, filled. So all sorts of coins, every coin imaginable, every bill, singles, fives, tens, 20s, 50s, hundreds, $1,000 bills, just filled. I mean, it would be impossible to count it. You could never count it in your lifetime. You could hire 1,000 people and have them counting your money, and they would never count it in your lifetime. So it's like, okay, it's pointless. We're not going to count it. Let's just call it a lot. But you can measure changes. So if you go to your giant money pit and you pull out $10,000, right? You didn't know how much money was in that giant pit. You don't know how much money is in there now, but you do know that there's $10,000 less in your money pit. Right, so you know that whatever amount you had, it just changed by $10,000, and vice versa. It works the other way. Like if you go in and you put $50 into your money pit, right? You don't know how much was in your giant money pit, but now you know that it's $50 more than it was, and you still don't know the final amount, but you know that it was $50 more than what you started with. So we can measure changes, and that's actually a pretty useful thing. So let me click this. Come on. All right, so this change in enthalpy. So even though, we don't know the enthalpy of the products, the enthalpy of the reactants, so this delta, again, delta means change. It's always final minus initial. So in a chemical reaction, you finally have products, and then you initially had reactants, so final minus initial. We don't know this. We don't know this. But we can measure this. How do you measure this? With a thermometer, as it turns out. It's actually really easy. It's the amount of heat that's gained or lost by a system at constant pressure. So when we're doing reactions in our lab, right, that's a constant pressure situation, right? Unless a tornado comes through and our pressure like plummets or something crazy, it's going to be a constant pressure situation. And we can measure this with a thermometer, basically. So something like methane and oxygen combustion reaction makes CO2 H2O. Bam, that releases a bunch of heat. So we can measure that, right? So 890 kilojoules was released in this reaction. All right, so we don't know the total enthalpy of the methane and oxygen. We don't know the enthalpy of the carbon dioxide and water, but we do know the difference, right? That was 890. So when I went from here to here, it dropped 890. It released a bunch of energy. And then also from this picture, it should be pretty obvious that if we went from CO2 to H2O backwards, so kind of reverse the equation, and made methane and oxygen from these guys, that would be uphill. That'd be 890 kilojoules up this way. All right. So delta H, all right. A process is endothermic when delta H is positive. So if you have a positive value for delta H, what that means is that energy is going into your system. All right. So heat's going into your system. Heat's flowing in. All right. And so if it's positive, if delta H is positive for endothermic, what do you think it is for exothermic? It's negative. All right. Also cool. Piece of cake. Screws onto this stuff. All right. This is called a reaction profile, an energy profile. The x coordinate here is sometimes the right reaction coordinate. It's basically a time. And this would be energy or enthalpy, really. So if you start off here and you got your reactants down here, and then your products are higher in energy than where you started, right? That's what we mean by it's an uphill reaction. It's an endothermic process. So heat had to go into your system. All right, so bam. So energy went in to form these products. All right, so that's uphill. It's an uphill profile. So what do you think exothermic is going to look like? Ta-da! So if you guess that, you guess right. So that means your reactants are higher in energy than the products. So when this happens, when reactants make the products, that extra energy, it's released. It's released into the surroundings. So exothermic reactions, they are downhill. Talk about that being a downhill reaction. Okay. The amount of energy absorbed or released in these reactions, we call that the heat of reaction, also known as the enthalpy of the reaction. All right. These are tabulated for lots and lots of reactions, actually. Kind of cool. Good stuff to know about enthalpy is that, number one, it is an extensive property. So remember what intensive and extensive meant. Extensive means it depends on how much you have. All right, so if I have 1 stick of dynamite, boom. If I have 100 sticks of dynamite, kabooey! Huge explosion, right? So if I have 1 mole of stuff releasing energy, if I have 10 moles of stuff, it's going to release 10 times as much energy. Right, so it's extensive. Very important to remember that. Delta H for reaction in the forward direction is going to be equal in size, but opposite in sign to delta H for the reverse reaction. Remember back to the methane and oxygen making CO2 and H2O. Right, in the forward direction, it was minus 890. All right, but if I reverse that reaction, if I start off with carbon dioxide and water and I make methane and oxygen, right, that would be uphill. 890. So a reaction that's exothermic in the forward direction is going to be endothermic in the reverse direction. So exo forward, boom, endo reverse. Or if it's endothermic in the forward direction, it's going to be exothermic in the reverse direction. So good things to remember. And this one here, last one here. Like imagine we have a combustion reaction. So the delta H for the reaction is going to depend on the state of the products and the state of the reactant. So the states of everything. But just for example, let's say I'm doing a combustion reaction and I had like methane plus oxygen making CO2, H2O, the same thing I've been talking about there. I'm going to calculate a different delta H if I use H2O gas instead of H2O liquid. All right, there's different amounts of enthalpy for those two different states. So you need to really pay attention to states in this chapter. All right, that's that little chunk, and I will catch you in the next one.